So the first problem wants the speed at that point. So we set up conservation of energy. So Ke equals change in PE. We can expand that out to 1/2 mv squared equal to mg delta h. Cancel out the m's. And we know that delta h is going to be this piece right here. So 1/2 v squared equals to g. And that's going to be the L here. So L, and that's going to be sine 25. And then solve for v. So it's 2gl sine 25. Square root both sides. We're going to get v is equal to speed. It's going to be 4.985 meters per second. Move on to part B. They want the net acceleration. So because the ball is going to be moving, we know there's going to be there's going to be an AC and as well as an A tan. So our AC is going to be pointing up, and our A tan is going to be the x component of our FG divided by m. So that means that we're going to have to set up for A total, and that's equal to the square root of A tan squared plus AC squared. So A tan is going to equal to G cosine 25, and that's going to be 9.5 cosine 25, and our AC is going to be V squared over R. We already solved for V earlier, it was 4.985 squared, that's over 3, the length of the string. Okay, now we'll solve for A total, plug everything in. So it's going to be 9.8 cosine 25 all squared plus 4.985. V is squared, and then we have the 3, and then we're going to square the whole thing. So our A total magnitude is going to be equal to 12.145 meters per second squared. On to part C. They want the magnitude of the angular acceleration. So we're going to need to find our A tan again. So our A tan is 9.8 cosine of 25, and that's going to simplify to 8.88 meters per second squared. We know that A is equal to R alpha, and alpha is going to be equal to A over R. So alpha is going to equal to A tan over R, which is equal to 8.88 over 3. And that's going to be simplified down to 2.96 rads per second squared. Okay, on to part D. They want the tension. So no, at the lowest point. So we know it's going to be an FC, that's the net. And we have a T pointing up and an FG pointing down. So it's we set up net force. So FC is equal to T minus FG. We want T, so it's going to be T equals to FC plus FG. Okay, we know that, and then we know that FC is going to be mv squared over R, and then our FG is going to be mg, and then they want the they want the tension at the lowest point, so we're going to have to solve for velocity again. And we can do that by setting up conservation of energy again. So we can do Ke is equal to change in PE. And we know that we went all the way down, so 1/2 mv squared is equal to mgh. Cancel out the m's. 1/2 v squared is equal to gh. V squared is equal to 2gh. Square root. V is equal to square root of 2, 9.8. We know that went down 3. So it's going to be V is equal to 7.668 meters per second. Now we can plug that into our T. So T is equal to the ball is 1.8 in mass. V squared is 7.668 squared over R is 3 plus 1.8 times 9.8. And so T will equal to 52.92 newtons. Okay, moving on to part E, was the velocity right after the collision. So we're gonna set up momentum. So Pi is equal to Pf. Okay, so that expands out to M1. Oh, my ball will be M1 V1I plus M2 V2I. And it says the collision is perfectly elastic. So we're gonna set up M1 again, V1F plus M2 V2F. Okay, so now plugging in some values, I know that the mass is going to be 1.8. V, it's going to be right before it hits it, so we can take our V from earlier, which is 7.668 plus 0.4 is the mass of the block, and we know that it starts at rest, so we can make that equal to 0. And we know this is going to be 1.8 V1F plus 0.4 V2F. Okay, just going to simplify my terms. We'll get 13.8 plus 0 is equal to 1.8 V1F plus 0.4 V2F. Okay, and we're going to set up KE after this, but before that I want to solve for one of the variables since I know how to plug it in. So I'm going to divide everything by 0.4 to make this easier. So we're going to get V2F is going to be equal to, it's going to be 34.5 is equal to 4.5 V1F plus V2F. And V2F is going to be equal to 34.5 minus 4.5 V1F. Now I'm going to set up my KE, my conservation of energy. So we know that KEI is going to equal to KE ball plus KE of the block. And we know this because since it's perfectly elastic, no energy will be lost. Okay, so I'm going to expand this out now. 1/2 M1 V1 V1I squared, and we know there's no M1 V, there won't be a KE of the block because it's starting at rest. So 1/2 M1 V1F squared plus 1/2 M2 V2F squared. Cancel out the 1/2s. Now I'm going to plug in my values. So I get, I don't know why I keep using that, 1.8. We know from earlier 7.668 squared is equal to 1.8 V1F squared plus 0.4 V2F squared. Okay, simplify this real quick. 105.84 is equal to 1.8 V1F squared plus 0.4 V2F squared. Okay, now I'm going to plug my V2F from earlier into here. So I'm going to get 1.8 V1F squared plus 0.4 on the outside. And inside the parentheses is going to be 34.5 minus 4.5 V1F. And we're going to square the whole thing. 1.05 here. Okay, now I'm going to FOIL. So 1.8 V1F squared plus 0.4. And when you FOIL this, we're going to get 20.25 V1F squared plus, no, sorry. It's going to be minus, because of the negative, so minus 310.5 plus, 310.5 V1F plus 1190.25. I'm going to distribute the 0.4 to all of these. So 105 again, 1.8 V1F squared. That's going to be plus 8.1 V1F squared minus 102.4. 124.2 V1F plus 476.1. Okay, I'm going to simplify one last time. Oops. Sorry. So 105.84 is equal to 9.9 V1F squared minus 124.2 V1F. And actually, I'm just going to subtract this over right now. Just kind of want to say room 0. So it's going to be just plus 370.26. And then I'm gonna put this into my calculator, set it equal to 0, and V1F is equal to 0 at V1F equal to plus 4.87734 meters per second squared. Meters per second. Okay, now for F, they want to know the time it will take for the block to come to a stop. First, I'm going to set up net force to find the acceleration of the block. And we know that the only force acting on it will be Fk once it's on the rough surface, which is equal to 0.4 A because it's M2. And we know that Fk is just going to be Fn μk, which is equal to mg μk is equal to 0.4 A, 0.4, 9.8. UK is 0.16. That's all equal to 0.4 A. Cancel these out. So A will be equal to negative, because gravity is going to be negative, negative 1.568 meters per second squared. On the left, on the right side of the page, I'm going to set up, we're going to also need the VI. So we're going to set up for V2F. And we know that's going to be equal to 34.5 minus 4.5 V1F, which is what we found earlier. So V2F is equal to 34.5 minus 4.5. Sorry, I don't know why. How many more by VF? We know that's 4.87734. So V2F is equal to 12.552 meters per second. Now we can use common form. So V2F squared minus Vf squared minus Vi squared is equal to 2A delta x. We want to know the time. We're solving for delta x here. So delta x is going to be equal to Vf. We know it's going to be 0, so negative Vi squared over 2A. We know the A is going to be negative 2, so we need to cancel these out right now. And we set it equal to, and that'll be that'll be just 12.552 squared over 2 negative, not negative, we already canceled that out, 568. Okay, simplify that to 50.24. Now I'm going to set up this equation, at squared, and then we'll solve for t, for time. That's what they're asking for. So we have 50.24 is equal to 12.552t. And I'll just put the negative in right now. Negative 1/2 of 1.568 t squared. We want this to be equal to 0, so we're going to get negative 0.784 t squared plus 12.552t minus 50.24. And we set that equal to 0. So this will equal 0 at t is equal to 8 seconds. Okay, on to part G. They want the angular speed now. They want the angular speed. So we can just set up Li equals LF. And it's gonna be the collision when it hits the rod. So actually we're gonna need new VF first, because if we see there, it says that the distance is actually gonna be 3/4 of the original distance, because if it was to full, it would just stop. So we know that so we can set up for new VF. We need to set up common form again. Sorry, so VF squared minus Vi squared equals 2A delta x. So you know that Vf squared is unknown, minus Vi squared, we know that is 12.552 squared. Equal to 2, we know the acceleration is negative 1.568. We know delta x is going to be 3/4 of 50.24. So we got this one earlier. So we put that there. And v2f. Wait, sorry. I mean, it is v2f, but we just keep it as vf here. vf squared is going to be equal to negative 118.1645. And it's going to be plus the vi squared is going to be 157.5527. Square all that. So vf is going to be equal to square root of 39.388, which is equal to 6.276 meters per second. And now that we have the vf, we can set up angular momentum. So li is going to be equal to lf. So cpr on the left side is equal to I omega, since we want to find the angular speed. Okay. So we know c is going to be 1. P is going to be mv. So cmv is r. So the m, we're going to plug in 0.4 of the block. The v, we're going to put in the new v we found, 6.276. And the r is going to be 2/3 of the length of the block, of the length of the rod, sorry, which is 5. We found, and we know that because it's going to hit and stick at 2/3 below the pivot. Or we know that it's 2/3 L, sorry. It's equal to 1/3. This is inertia now, 1/3 ml squared. It's the rod. Plus m. And then since the point mass is going to be mr squared, and we know the r is going to be 2/3 because this is from pivot to the point mass. L is going to be squared together, and then we square the whole thing. So we're not going to square the whole thing. What am I saying? Omega here. Ugly. Omega. Actually, I'm just going to plug this. I'm going to plug the values in right now. 1.3, 1.1, 5 squared, plus 0.4. So it's lowercase m. 0.4. And then we get 2/3 times 5. And that's all squared. Omega. Now I'm going to simplify. So on the left side, we'll have 8.368. And the right side is going to simplify down to 13.6 omega. And omega is going to be equal to 0.6148 rads per second. It's going to be English speed. Sorry, we have h. Here they want the height. So we're going to set up for... we're going to set up conservation of energy. But before that, I'm going to find the KE rod. So KE rod, because when the block hits the rod, it will not move linearly, but just have a KE rod instead of a KE lin. So it's going to be 1/2 I omega squared, and that's going to be equal to 1/2. We found that earlier to be, we found the I of the whole system earlier to be 13.6. And then omega squared, sorry, you can plug that into, you know, omega 0.6148 squared. And that's going to be equal to 2.5723 joules. And we can, I did this first because now we can set up conservation of energy is PE, the PE final, which is when it's going to be its highest height. It's going to be equal to the KE initial, which is the KE rod. So it's going to be mgh is equal to, we found that earlier, 2.5723. Isolate for h. It's going to be 2.5723. And actually this m is actually going to be m new. Sorry, new. Because it's going to be a new block. It's going to be the new system as a whole. So it's going to be 1.1 plus 0.4. So we have 1.1 plus 0.4 on the bottom. And then the g is going to be 9.8. And that all simplifies down to 0.175 meters. Okay. Now we're on the last one. It's going to be I. So here I can just set up angular momentum. Angular momentum. And that's going to be Li again equals Lf. It's going to be for the new system, where L is going to be L over 2 instead of 2/3 L when it collides. So same thing, CPR is equal to I omega. MVR is equal to I omega because C is just 1. C is 1. Okay. So now we can start plugging in our values. So this M here is going to be the block, so 0.4. The speed is the same, 6.2. Let's go up. 6.276. 6.276. The raw is going to be, the R is going to be L over 2 now, which is 5/2 instead of 2/3. So you go to I omega. So the I is going to be 1/3 ml squared plus, I'll just plug it in right now. Actually, I won't, sorry. ml squared, there's a capital M, so plus M, and the R now is going to be L over 2. L over 2 squared omega. Okay. I'm gonna plug these in now. And this is gonna be of the raw, so 1.1. L is still 5 plus 0.4 of the block. And now it's gonna be 5/2 squared omega. And when we simplify all this down, it's gonna be our F final. Sorry. It's gonna be 0.54 farads per second. That's speed, because we can just compare the speeds, and we know that the old one, the F1 from earlier, 0.6 something, so 6148, and that's greater than 0.54. So therefore, the new angular speed would decrease.